In this video, we are going to discuss the resonance effect on the acidity of organic compounds. I have prepared a bunch of examples to illustrate this effect on the strength of the acids in organic chemistry. But before going over that, we should discuss basic definitions about the conjugate acids and the conjugate bases. Here we have a set of halo acids. We know from basic chemistry that hydroiodic acid is the strongest acid out of them, and hydrofluoric acid is the weakest acid out of them. For example, when hydroiodic acid dissociates into a proton and iodide ion, this iodide ion is called the conjugate base. And this proton is called the conjugate acid. And this applies for all other acids. The fluoride and chloride and iodide and bromide and iodide ions are called the conjugate bases of the corresponding acids. And all these protons are called the conjugate acids. The reason why hydroiodic acid is the strongest out of them is due to the stability of the conjugate base, which is the iodide ion. As the stability of the conjugate base increases, the acidity or the acid strength increases. When we take a look at this iodide ion, the negative charge on the iodide ion can be distributed over its large size. So it's the strongest acid out of them. But in case of the hydrofluoric acid, this fluoride ion has a small size, and this charge is concentrated on this small size, so the ion is not happy to carry this additional negative charge. So the stability of this ion is low, so the hydrofluoric acid is not a strong acid. So we can conclude that the more stable the conjugate base, the stronger the acid. Back into our examples, this is an unsaturated alcohol, and this is phenol. We want to compare the acidity of both compounds. In the first unsaturated alcohol, when it deprotonates, it gives us this conjugate base. And in this phenol, when it deprotonates, it gives it the phenolate ion. So in the conjugate base of the first compound, this negative charge on the oxygen can make a double bond between this oxygen and the carbon right here. And this bond can move into this carbon, giving me another resonating structure. So we have two resonating structures. So this negative charge can be distributed over two atoms, which makes the conjugate base a little bit stable. But in case of phenol, here this negative charge can be distributed over many other carbon atoms as follows. This negative charge can form a double bond between this carbon and oxygen, and this double bond can move into this carbon, forming here a negative charge, and this double bond can move to this carbon, forming a negative charge like that, and this negative charge can form the double bond, and so on. And in the end, we get four resonating structures. But in the first example, we have two resonating structures. And we know that the more resonating structures, the more stable the compound, so it's more acidic. So phenol here is more acidic than this unsaturated alcohol. Another example here is the propanol and this propionic acid. When both of these compounds deprotonate, they give the corresponding conjugate bases. And here we want to know, or we want to compare their stability, or the stability of the conjugated base of each of the following compounds. Here in this compound, or this conjugate base, we've got the negative charge here is concentrated on an oxygen atom, so there is no conjugation or no resonance can occur. So this negative charge or this negatively charged oxygen is not happy with that charge. So it makes the conjugate base less stable. But in case of the conjugate base of the carboxylic acid here, in this case, the negatively charged oxygen can donate its electrons to form a double bond between this carbon and the oxygen, and this bond can go to this oxygen forming a negatively charged oxygen. So we get two resonating structures. So this conjugate base has two resonating structures, and this has 0 resonating structures. So it's obvious that this conjugate base is more stable than that. So this compound or this carboxylic acid is more acidic than this alcohol. A final comparison here between a phenol and a carboxylic acid. When they deprotonate, they give the corresponding conjugate bases. We know that this phenol has 4 resonating structures, and this carboxylic acid has 2 resonating structures. And the negative charge on this phenolate ion is distributed over this oxygen and the carbon right here, and this carbon and the carbon right here. But the negative charge here on this conjugate base of the corresponding carboxylic acid is distributed over this oxygen and that oxygen. So it may come to your mind that as this phenolate ion has 4 resonating structures, so it's more stable, as this conjugate base has only 2 resonating structures. But keep in mind that quality is better than quantity. In other words, when an oxygen bears a negative charge, that's energetically favorable than a carbon atom bearing a negative charge. So the stability of this conjugate base is higher than the stability of this phenolate ion. So this aliphatic carboxylic acid is stronger than this phenol. And that's it. I hope you enjoyed the video, and don't forget to subscribe.